Our first paper is an efficient approach to playback of stereoscopic video using a wide field of view. And we have two speakers. Professor John LaDisa is Associate Professor of Biomedical Engineering at Marquette University, where he directs the Visualization Laboratory, also known as MARVL. Chris Larkee is the Visualization Technology Specialist for Marquette. His work combines a background in video production, motion graphics, broadcast engineering, and graphics programming. Gentlemen.
Thank you very much for the opportunity on behalf of Chris and myself, the opportunity to present our work with you here today. So the backdrop for what we're discussing here is our large-scale immersive environment and several other stereoscopic or active 3D displays that we have as part of the MARquette Visualization Lab, or what we refer to as MARVL. So MARVL really contains these resources dedicated to not only research and teaching, but also industry and outreach initiatives. We have the large-scale immersive environment that you see here. This is a sort of a slightly different twist on the traditional cave. So this is an extra wide, four-sided cave. So it's about 20 feet wide, 10 feet tall, and 10 feet deep, and that was dictated by the end users that came forward during the planning portion of putting this cave together. Everything is back projected except for the floor. So we've got four projectors across the front. You'll see the specs on those in just a minute, two per side, and then two for the floor. We also have adjacent to this what we call the CDL, or the Content Development Lounge, where the content that you'll see today is created. We have the ability to test the content there before we move it into the cave. And then down on the right, we have a hollow screen or another 3D, active 3D display system that we can also use outside of the CDL. We opened about 2 years ago, and over the course of that period, we've provided academic experiences, so at least hour-long experiences for roughly 1,000 students from 24 different classes and in 10 different disciplines across campus. So we're a lot of things to a lot of people. If we look at sort of all comers to the lab over the last 2 years, we estimate that we've had about over 4,000, maybe close to 5,000 people through the lab. The other thing that's not presented here is the work that we're doing with head-mounted systems, headsets, Gear VR, Oculus Rift. We really use those purely as ways of showing our content in a portable manner. So when people want to collaborate with us, but they can't always get to the cave, we'll use this as a way of delivering that content. Here are some specs of our MARVL large-scale environment. We've got 10 Christie projectors. You can see the specs there. Again, 4 on the front wall, 2 per side, and 2 on the floor. This is run by 6 HP workstations. Again, you can see the specs of those up on the screen. So those are some constraints for us, right? We have a cluster-based system, and they figured into our objective here on the screen today. Our end-user applications as well, they required a couple things. One was the ability not only to display the content, but also interact within it. And most of the content we'll be talking about today is forward motion video that we obtained at a constant rate. Our 4K resolution is our front wall in our cave, and we've got about 7K overall if you consider the sides as well, and we have high frame rates that we need to deal with as well. So this set the context for our application, that is to develop an approach to playback of stereoscopic videos in a 3D world where we had the depth actually determined by the content.
Okay, so all of our programs that we've been making in the cave over the past 2 years have all really been using the Unity game engine. So our traditional workflow is to build virtual environments using things like 3D meshes, polygons, lights, and use that type of rendering workflow. But so to do something that's completely video-based, but still keep it inside Unity was actually something that's a bit of an unusual combination. And we managed to do a couple of tricks that we figured out that I'd like to share with you. So the workflow to creating a video player inside Unity is actually not terribly unusual. We're making 2 cameras and 2 screens, and basically configuring it so only the left camera can see the left screen and the right camera can see the right screen. But in order to actually pull it off and run it on a cluster on a 7K projection display, all in sync, there were some challenges that went into that. So another reason we kind of had to customize the player is because our content was rather customized. So this is just a sample frame of the kind of things that our students were producing. This was captured using a 6 GoPro camera rig, using a camera mount that the camera rig that they 3D printed and designed themselves. So it's not your typical spherical stereo rig. This is actually a cylindrically projected panorama that only covers about 270 degrees horizontally. So the reason it's not completely spherical is because that field of view really kind of matches what you see in the cave typically, because caves have an open back and things like that. So that's stereoscopic with left on the top and right on the bottom. So to start off, we had to create a custom screen, and the tool of choice that I used here was Blender, which was really what we used to make a lot of our programs. But the modeling for this scene was just really make a custom screen. And for this one, you're going to need your 3D glasses to see a sample of the kind of screen that we created. So it's really just a sphere that has a portion of it cut off. The top and the bottom are cut off, and then it's open in the back. Now, this is just one version that we've done. We've also done other versions where we've mirrored completely the physical models of the cave for a more precise alignment, but this one is a cylinder, basically. Also, equally important is the UV mapping on this, which we tune quite a bit to make sure it matches the custom rig the custom content. So this is a view, sort of a simulated version of what you see in a headset. Now, this isn't completely accurate because it's not a direct capture, because what this is really just a cropped version of the spherical panorama that I showed you earlier. The proper version would be projected onto the sphere, so the aspect ratio would be a little bit more correct. And also, because this was the student's first attempt, there's also some various issues, most notably the frame line at the top and the bottom. Most of that is outside of the field of view when you're viewing it inside the cave, so it's not quite as flickery as you see it here. And this is a screenshot of the arrangement in Unity. So as you can see, my hierarchy is really quite simple. I have 2 cameras and 2 screens. The screens you see are mirror copies of the same object that just are using Unity's tagging system to specify whether it'll be visible in the left eye or the right eye only. But what I'd also like to point out is some detail I have on the right side, because that part is rather important to making this work in a high-performance way. Starting from the bottom there, the movie script is a custom script that I wrote that does various things like user inputs to play and pause the video. It also maintains some cluster synchronization code in there. But above that is the main video decoder. Now, one of the main keys that makes this work is that we're taking in the video frame once, decoding it once, and then copying the texture data onto 2 separate objects. We use that by having the apparent object in the movie hierarchy, and then the 2 screens below that. Most other documentation would have the movie player and the texture updater component on the same object. But that didn't work for us, because then you're decoding and moving the video texture through memory twice, which is really problematic when you're dealing with 4K footage. So to summarize that, 2 copies of the object. They're on separate layers, labeled left and right only. And there's a couple other things that I think are also nice about this program. One of them is that in order to make the program a completely reusable video player, I did write some additional features to have it read the locations of the video files from an external file, which can be edited without having to recompile the program. And the other thing is, even though we're inside Unity, we're using an unlit shader just to get the video texture directly on screen without having to compute lights or shadows or anything like that. Again, that's for performance, although we do have enough performance to spare on our system that we can do some hybrid stuff. The camera masks are a little bit unusual, because the ability to have objects flagged per eye is actually something that only was added recently, starting with Unity 5.1, which really started to focus on VR extensively. So for the Unity 5.1 and onwards, we're using part of the predefined Oculus prefab object for our camera rig. But we did have this working on Unity 4 using some steps I'll show you in a moment. So in order to run Unity on a cave, there's a number of additional pieces that are required. The one that we use is called MiddleVR, and this handles things like the infrared tracking system, the clustering, the off-center camera projections, and various inputs like that, cluster management, and all the things that are missing in the default build of Unity. So the thing about MiddleVR is that the camera rig is loaded from a configuration file that's built at runtime, so we have to set everything up through script. So I've included a little piece of code here just because the ability to uncheck things inside a menu is not something that's really well documented in my opinion. So you actually have to deconstruct an object in there. So now one of the things that I think was also really beneficial that we kind of discovered the hard way was that the traditional default camera setups have, obviously for stereoscopic you have camera separation, but that was actually producing a conflict for us because we were getting too much stereo. Because that worked for our first attempts with video where we had the video on a small surface where it was inserted into the scene and playing on only a portion of your field of view. But if the movie plane is the entire scene and wrapping around you, then when the camera rotates, there's just the stereo is incorrect. So what we've done here is that we have a specific configuration where the camera separation, the eye separation for the two cameras is set to 0 because the movie file itself already has the cameras pushed apart. So in order to make them conflicting or not exaggerated, we actually have a simplified approach for that. So this is also also another early attempt that didn't work was trying to inject the two objects directly into the quad buffering rendering pipeline, but that was pretty unreliable. So this is kind of an example of the kind of content that we've been showing with using a combination of photos or videos in our cave. I'll hand it over back to John to describe what we're looking at here.
This is probably our most commonly used application currently. So this is what we started as an immersive fitness program through the lab. And we bring this up to show a couple of different things. On the left, you can see an implementation that we did locally following some success in MARVL. On the top right, with your 3D glasses, you can see in this particular case, we're moving through forward motion video, or still of at least moving through forward motion video. But on the right, as an application of the custom UV mapping that Chris was talking about, on either side of the screen, actually, there's some distortion that's been implemented to give the rider a sense that they're moving through the space at an increased rate. In contrast, on the lower left, for the immersive yoga program that we're running, that's just simply wrapped around the full 7K, available 7K resolution. And again, this has been something that was a challenge to work through and led to the developments that Chris has talked about, but has also been hugely popular at our system here.
Also, these applications are a really good demonstration of why we're doing it in Unity at all, instead of just a dedicated video player. Because as you can see on those screens here, we're not just playing a video. We try to bring a lot of interactivity to them. So by doing it in a flexible game engine, we can have live overlays, integrating live data. We can have do a lot more interactive things with our audio, including spatially positioned audio. We can have custom timers or modify the playback rate, which is something that's very useful for these workout videos. We have another student working on a system where we use a Bluetooth sensor on the bicycle to control the playback rate of the video. And basically there's a lot of other clips. Another one that we've done that's not pictured here is a basketball simulator where we can test the reaction time of a person's ability to predict the direction that a player is going to move, either to the left or to the right. So these applications are kind of being used to conduct other experiments and other experiences.
The other one we wanted to feature here, and this feeds nicely into the portable version, our head-mounted devices, is an architectural pre-visualization, and we also have a historical realization program. This is part of an ambitious program by the university, over a $100 million project to try and raise money for a research center. So we begin bringing stakeholders into this space and helping them to appreciate what it would look like, and again, taking advantage of a lot of the advancements that Chris has made. Here again, you see a crop from a spherical panorama rather than what you would see in the head-mounted display.
And so this is using the same technique that, because it's a pre-rendered 3D render, this actually took several hours to render on a machine. But because it's all pre-rendered, we can render that take that rendered image and run it on mobile. So this is the same technique, the same stereo setup, but running on a Gear VR headset instead of running in a full cave.
Go ahead, Chris.
Oh, it's here. So another missing piece in this to really achieve high-performance video playback inside Unity is this third-party plugin called AV Windows Media. Unity does have some capability of doing movie textures built in, but it really doesn't have the level of performance that we require to have full-screen resolutions at 1080p or above. So a lot of the stuff we run is 4K, which really requires a GPU-accelerated decoder. So that's really what AV Windows Media Pro does. However, that doesn't really solve all of our problems because there's still some finesse required in order to get a proper playback, a smooth playback rate from that. So part of the reason was well, these are just some of the features of AV Windows Media Pro that we liked because I think I probably covered that earlier. So getting the video format in a way that we preferred was actually really quite challenging. And one of the tips that I would have for you is to use the XVID codec. XVID is actually a pretty ancient media codec compared to others. It's a predecessor to H.264. And the simplicity of it is actually its strength for doing this type of playback because it's so simple. It can decode 4K resolutions very quickly, even though it's never really designed for 4K. And because it's not efficient, it actually requires a very high bit rate of around 80 to 90 megabits per second. But that did actually allow us to achieve the frame rates that we needed. Whereas with H.264 or H.265, the bit rates were lower, but it still started to keep in sync along the cluster.